there was an error as I had this thing. We see here that the angular velocity goes from 0.60 radians per second to 0. I had omega bar, average omega, was about 0.20 radians per second. It's about 0.30 radians per second. Small arithmetic mistake there. And then everything followed from that, and everything that followed down to this point was incorrect. So let's see what we have. Average omega is 0.30 radians per second, but we don't really even use that. The change in omega is from 60 to 0, or negative 6.60 radians per second. Then we can calculate the average acceleration as the change in omega over the time interval. Time interval is 3.02 seconds. This gives us an approximate angular acceleration of negative 0.20 radians per second squared. Now there's an alternative way of calculating this. We know that the thing accelerated from some angular velocity to 0 in a delta t of 3.02 seconds. And that in doing so it went through an angle that went from the 0.38 radians where the washer hit the table to the 1.13 radians where the beam stopped. So that the angular displacement between those 2 points is only 0.75 radians. So we traveled 0.75 radians in 3.02 seconds. That tells us that the average angular velocity must have been about 0.25 radians per second. And then we can use this, of course, to find the final angular velocity, or in this case, the initial angular velocity. And that's going to be double the 0.25 radians per second, or 0.5 radians per second. And the change in velocity will be negative because we're going from a positive velocity down to 0. So we're going to have negative 0.5 radians per second change in velocity. And we divide that by the 3.02 seconds, and we get something that's pretty close to negative 0.17 radians per second squared, which is in fairly good agreement with the negative 0.20 that we got up here. So there are two ways to approach this again. One is using the final velocity we obtained from the first phase. The other is ignoring that and just using the data that we have for the second phase. The displacement, the final velocity, and the time allows us to calculate the original velocity and the acceleration. Once more, we see pretty good agreement here. Now if that kind of agreement holds up, it's pretty good evidence that the acceleration in this system is either uniform or very nearly uniform. And it also gets us used to the idea that the reasoning that we've used with velocities can be extended to angular velocities.